G'day, my name's John Steele from the University of New South Wales. This is next in our series of videos on complex analysis. In this video I want to look at harmonic functions. A function from R2 to R, so taking two real variables and giving a real number out, is said to be harmonic if it satisfies this differential equation here, partial d2u dx squared plus partial d2u dy squared equals 0. This is known as the two-dimensional Laplace equation, after the French mathematician Pierre-Simon Laplace. But it must also satisfy this little condition here, that these second-order partial derivatives are continuous. Now, it might seem a little odd. Why would we look at real valued functions in a course in complex analysis? Well, it's because harmonic functions have a very deep link to analytic functions, which are very important in complex analysis. We've got two little results here I've put in blue. If you've got a complex valued function f, written in real imaginary parts as u plus iv, if f is analytic, then u is automatically harmonic. In fact, v is harmonic as well, but we normally concentrate on the real part. And the second result goes in the other direction, really. If u is harmonic, then there is a v such that u plus iv is an analytic function. We call this function v here a harmonic conjugate of u. It's not unique, but any other harmonic conjugate only differs from v by a constant. So if you're given a harmonic function u, you can find a whole family of analytic functions f, but they all differ by just an imaginary constant because you just add a constant to v. Now, what you normally look for in these sorts of problems when you're asked them in a test or exam is you're given a u and asked to either prove it's harmonic or not, usually not, and then to find a harmonic conjugate, v, and then perhaps write u plus iv as a function of z. So u and v are given in terms of x's and y's, and we want to combine everything together so everything is just in terms of z. So what we're going to look at in the second half of the video is how we do that. How do we find a harmonic conjugate given a harmonic function u? All right, so this is the sort of problem that you might get faced with. I've picked a particularly simple harmonic function here, just to show you what's going on, because it illustrates everything without having any particularly difficult integrations involved. Given that u equals xy is harmonic, you want to find the harmonic conjugate and write harmonic conjugate v and write u plus iv as a function of z alone. Well, it's not hard to prove that xy is harmonic. It satisfies Laplace's equations, quite straightforward. d2u dx squared and d2u dy squared are in fact both 0. But we're not asked to prove that. So the question is, how do we actually find a harmonic conjugate? Given u, how do we find a v so that u plus iv is going to be analytic? Well, the clue is in the two problems, the two theorems I've got written up here. If we've got u and we want u plus iv to be analytic, well, that means that u and v together have to satisfy the Cauchy-Riemann equations. So those are the partial differential equations, in fact, that u and v must satisfy. We know u, that gives us one side of the partial differential equations. We've just got to find v. Right? And once we've got that, we can write down at least u plus iv. We can write f in terms of x's and y's. All right, so let's write down the Cauchy-Riemann equations. V must satisfy, well, du dx, which is of course y, must equal dv dy, and the other Cauchy-Riemann equation is that du dy, which in our case is x, is minus dv dx. So we now have our two partial differential equations, and what we choose to do is to integrate them. Now you can do this in several ways, or two ways I should say perhaps. You could integrate them both and compare, but I think the best way of doing this is to integrate one of them, introduce an arbitrary constant which is a function of the other variable, then differentiate that sort of partial version of v back and fit it into the other one. Now, which one of the equations you integrate depends on the problem. Pick whichever one looks easiest. In this case, it's really much of a muchness. I'm going to choose to integrate dv dy equals y, but only because there's no minus sign there. No other reason. All right. Then v will integrate y with respect to y, and we get 1/2 y squared plus the arbitrary constant. Remember, solving a differential equation, you cannot forget the arbitrary constants. In this case, it's actually an arbitrary function, but it's a function purely of x. And my advice to you is to write that dependence down. I'll explain that in a minute. So if that's what v must look like, we're going to find out what phi is by comparing it to the other equations, the other partial differential equation. It follows that dv dx is just going to be phi dashed of x. Now that's to equal minus du dy, which is to be minus x. And notice this is a function purely of x, which is as it should be. If you end up with a problem here where this is a function of x and y, you've made a mistake. So go back and fix it. So since phi dashed of x is minus x, phi must be minus 1/2 x squared plus some arbitrary constant. Well, the question only asked us for a harmonic conjugate, so we don't need to bother with the arbitrary constant if we don't want, and we'll decide to not want. We'll just not bother. So we can take phi to be minus 1/2 x squared, and so v is 1/2 y squared minus x squared, and u plus iv is xy plus 1/2 I into y squared minus x squared. Well, the last thing we've got to do is to rewrite this as a function of z alone. Now with this particular question, it's quite simple, and if you've been playing around with complex functions for a while, you'll be able to spot exactly what the answer is. But there is a nice little trick, it's almost a magic trick really, that allows you to write this thing down, to write f as a function of z in much more complicated cases. Now, I'll point out that when I lecture these courses, I usually discuss this idea, but not everybody does, so be aware of that. And it's a trick known as analytic continuation. Well, it's not a trick, it's a theorem. And it's a property of analytic functions. Complex analytic functions are wonderful creatures. And the particular wonderfulness we're talking about here is that if you've got two analytic functions that are the same on some interval along the real axis, then in fact they must be the same everywhere. So what does this mean in practical terms for this example? Well, what it means is that if we were to look at this function along the real axis, which would be setting y to be 0, what will we get? Well, we'd get minus 1/2 x squared. So you ask yourself, what analytic function looks like minus 1/2 x squared along the real axis? Well, minus 1/2 z squared would. Right? And that, in fact, is the correct answer. Analytic continuation tells you that that would work. You set y to be 0, change x to z, and that's the correct analytic function. And that will work for every analytic function, but only because it's analytic. So what we get out here is minus 1/2 I z squared. Now, it is also possible, in fact, to use this idea of analytic continuation to short circuit most of these calculations. And for certain problems, it's easy to do that, not perhaps for this one. So what I'm going to do is show you another example, which would be very difficult to do in this way, but in fact works out quite nicely with analytic continuation. All right, so here we have another example. I'm going to try and find a harmonic conjugate for u is x over x squared plus y squared. Again, you might recognize exactly where this has come from, but if not, well, you'll be faced with quite a lot of tricky calculation if you imagine differentiating this thing with respect to x and then integrating the resultant mess with respect to y. Not going to be a lot of fun. However, with analytic continuation, we can get the whole thing out really rather quickly. And the idea is as follows. If f is u plus iv and is analytic, then Well, its derivative, f dashed ux plus I vx. Well, that's also analytic. That's the result you come up with later on in the course, perhaps. But the Cauchy-Riemann equations tell us we can replace Vx, this is a shorthand for dv dx, we can replace that with dv dy, or minus dv dy, I should say. So this is the same as ux minus I uy. And we can calculate this thing just knowing u. And then we could use analytic continuation to write ux minus I uy, in other words, f dashed as a function of z, and integrate the resulting thing with respect to z alone. So in this example, f dashed is, well, differentiate this thing with respect to x, and it's a quotient, and we'll see just how unpleasantly messy it is. We're going to get 1 times x squared plus y squared minus x times 2x squared divided by x squared plus y squared all squared. So that's the thing you would have to integrate with respect to y, to do it the other way, minus I times, well, the derivative with respect to y is a bit simpler. It's 2xy over x squared plus y squared squared. So that's f dashed as a function of x and y. What does our analytic continuation trick tell us? Well, it tells us that this as a function purely of z, well, we just need to set y to be 0 and change the letter x to z. Well, the 2xy, I, that term on there, that just disappears. What do we get over here? Well, we get x squared minus 2x squared. We get minus 2x squared, which will become 2z squared. And on the denominator here, we get z to the 4th. In fact, we don't get the 2 there, of course. Sorry, we just get z squared. So this is minus 1 upon z squared. Well, if f dashed is minus 1 upon z squared, f must just be 1 upon z. So u, x over x squared plus y squared, must be the real part of 1 upon z, which in fact it is, if you remember how to take the real part of 1 upon z. So a harmonic conjugate would have to be the imaginary part of this. And the imaginary part of 1 over z is then minus y over x squared plus y squared. And that's the problem solved.